Welcome students. We want to discuss about method of Lagrange multipliers. So this is for optimization. Before I start, I would like to read this quote by Joseph Louis Lagrange, the founder of Lagrange method, but he was also a well-known mathematician. So as long as algebra and geometry have been separated, their progress have been slow and their use is limited. But when these two sciences have been united, they lend each mutual forces and have marched together towards perfection. It's quite profound. And note that this quote was said before 1813 when Lagrange died, right? After that, there was the huge boost to the area of algebraic geometry, which led to a lot of interesting results in mathematics. Okay, so with that, let's try to see what this optimization method is about. So consider the following problem. So find the point on the parabola y equals to x minus 1 square that are closest to the origin. So the point, so suppose you have a point here, xy. So the distance of this point, d, is going to be square root of x squared plus y squared, right? So you want to minimize this distance, d. Well, d is also a function. You can think about d as a function of x and y, right? If you change x and y, you get different d. So we have d of xy equals to square root of x squared plus y squared. So note that the point with the minimum of this function on its own is just the origin 0, 0, right? Because that is the closest point to the origin, namely itself. But along with that, we have one more restriction or constraint. This is called constraint, restriction, constraint. The constraint is that this point should come from the parabola. So the point cannot be arbitrary, but it has to come from parabola here. So this, in this case, g of xy, you can call this as, this is, say, y minus x minus 1 square equals to 0. So you want to basically minimize function d of xy, but with constraint. What is the constraint on xy? Xy cannot come from anywhere, but they come from the parabola, namely that with constraint g of xy, which is this curve, equals to 0. So these are the kind of problems we are going to deal with Lagrange multipliers. Yeah. So the idea is, again, you have a function and you have a constraint curve, which basically restricts a kind of point you can choose for maximum or minimum. So let's look at it formally. So we'll start with the function of two variables. So Lagrange multiplier for two variables. Let f of xy and g of xy be continuous function with continuous first order partial derivatives. We are assuming the function is nice. Now, if the maximum and minimum value of f subjected to the condition is that g of xy equals to 0. That means x and y are coming from g of xy equals to 0. They occur at a point P where grad P, if grad P evaluated at g is not 0, then grad f equals to lambda grad P for some constant. So what is it telling us? It's telling us if you want to look for the maximum or minimum of f of xy, subjected to constraint that g of xy is 0, where do you look for those points? You look for those points in the following equation. So those points are the points which will satisfy the following. That is grad fp equals to lambda grad gp. Okay. So the associated values of lambda are called Lagrange multipliers. Now let's see why geometrically this is true. So consider f of xy. We want to optimize f of xy. And the constraint is what? That g of xy is 0. So g of xy is some equation which your xy should satisfy. So suppose it looks like this green curve here. So this is your g of xy equals to 0. So g of xy equals to 0, this is your constraint curve. That means your x and y should come from here. Now consider the following. So let's look at the following point. So f of xy equals to 1 is this level curve, f of xy equals to 2 is this level curve, f of xy equals to 3 is this level curve. So this is increasing, right? This order. So now consider the point Q. Now at point Q, we have, well, at this point Q, of course, the maximum or minimum subjected to this constraints must come from what? Must come from the intersection point. What do I mean by that? If we want basically that f of xy to be maximum or minimum subjected to g of xy equals to 0, then that point should come from the intersection of both the points, right? Because it's a maximum and minimum value of this function, so it should lie on this. And because our constraint curve already to start with is g of xy equals to 0, so it should lie on that. So we are looking at essentially the intersection and seeing where, on which intersection is the function f value is maximum. Yeah. So clearly, I mean, so here, if you look at this point here, so what is the direction of grad f? So the direction of grad f is going to be, so this is your f of x equals to 1. So the tangent line to f at q will be given by this. And then the grad f is perpendicular to that. Like it's a normal, right? So same way for the surface curves, we also had the same thing, right? For surface curve, we had, if we had a surface like this, you had z equals to f of xy. The grad f was basically the normal, right? Tangent to this, sorry, perpendicular to the tangent plane, right? So same thing about function of two variables here. When you're looking at the level curves, your grad f, so you basically draw a tangent at this point for your function f, and your grad f will be perpendicular to that. Similarly, what is happening for the function g? So for g, at this point, this is your tangent, and this is the perpendicular to it, right? So this is the direction of your grad g at q, my bad. So in this case, you can see that grad g at q and grad f at q are not parallel, and you can see that this is not going to be the maximum or minimum of the function either. So this means that if they are not parallel, this means you can move a little bit further ahead. You can find another level curve for function f for which the value will be bigger than 1. Yeah, according to this graph, of course. Moving in this direction doesn't mean that it will increase, but according to this graph, it will basically, you will move bigger than 1, and you'll be still on the what? Still on the constraint curve at this point. So therefore, you haven't reached maximum at q. So the maximum is reached at p when both of these level curve and the constraint curve intersect. In that case, what we have is, this is a common tangent line, and the normal to the curve g is given by grad. This is my grad g at p, grad g at p. And similarly at this point, my grad f at p is also, so for the function f of x, this is also going to be tangent to the level curve f of xy equals to 2, and you see that this will be also the direction of grad f at p. So this is essentially the setup you have. At p, there's a common tangent to both f and g, and hence there's a common normal. So the normals are perpendicular, right? Normal vectors are perpendicular. So this is where the maximum or the minimum appear. In this case, the maximum appears at this point, right? So such a method of optimization is called Lagrange multiplier. All right. So let's look at an example. So essentially, what are we solving? We are looking for, the idea behind the optimization is you achieve maximum or minimum is achieved when grad f equals to lambda grad g subjected to constraint what g of xy equals to 0. So essentially you're solving the following system of equation. First of all, g of xy equals to 0 because your x and y values should be satisfying the constraint curve. Because of grad f equals to lambda grad g, you will have fx. So you have, this is your grad f, right? So grad f is fx, fy, grad g equals to gx, gy. So when grad f equals to lambda grad g, this means that fx should be lambda grad gx and fy should be lambda grad gy. So the point which satisfy these constraints, or these equations together, I should be not using constraint words to get often. So the points which satisfy these three equations are your possible location for extrema, all right? And then you compare to get maximum or minimum. All right. Note that you're not looking for absolute maximum of the function here. Let me go back again and digress on that point again. So the idea is perhaps the larger value of f is somewhere here. Yeah, this will be the larger value of f, but it doesn't lie on the constraint curve. So you are looking to maximize f at those points which lie on the constraint curve. Okay. So let's look at the following problem and work it out. So find the maximum and minimum value of this function f of xy subjected to the constraint 4x squared plus 9y squared equals to 36. So first of all, this is my the function I want to optimize. People call it objective function as well. If you want to give it a name, objective function to optimize. And this is the constraint curve. So note that you can call this as g of xy equals to 4x squared plus 9y squared, either equals to 36 or subtract 36 and make it equal to 0. It doesn't matter. You can use either one of them. So first step is what? So solve for grad f equals to lambda grad g. So what is grad f? This implies grad f is going to be partial derivative of f with respect to x will give me y, partial derivative of y with respect to xy with respect to y will give me x, equals to lambda times grad g, which will give me, if I take derivative of this, I get 8x, and partial derivative of g with respect to y will give me 18y. So from here we get, this implies we get 8, and also we need this thing, we get y equals to 8 lambda x, then we get x equals to 18 lambda y, and then of course we have another equation which is g of xy equals to 0. So this is the equation. So three equations we need to solve. We need to solve these, need to solve. So how do we go about it? So the idea is we'll take these two and substitute in this equation and solve for. So now we can assume that lambda is not 0. Lambda is not 0. If that's the case, else x and y both are 0, right? Because of these equations, both are 0, and that will not satisfy the constraint curve, right? Constraint. Not satisfy g of x. Let's put it this way. So not satisfy g of xy equals to 0. Because in g of xy equals to 0, you have 4x squared plus 9y squared minus 36 is 0. If x and y are 0, then it will be minus 36, not 0. Okay, so from there, we'll try to solve for this now. So we have, let's see. So if we divide both, say, let's say y by x. So now we have to solve uh, this set of equations. So I would like to get rid of lambda. So the way to get rid of the lambda is I'll divide y by x. Note that you can do it other way. Other ways to do that. There are other ways to do the same problem. We have 8x divided by 9y. So this will give me, sorry, 8x divided by 18. So 8x, so we get 4x divided by 9y. This will give me 9y squared equals to 4x squared. So then I can plug this one of these in this equation. So instead of 4x squared, I can write 9y squared there. So, and substitute it in g of xy. We get what? We get, say, if you want to do 4, if you want to substitute for 4x squared equals to 9y squared, we get 9y squared plus 9y squared equals to 36, which give me y squared equals to 18. So 36 by 2, which is going to be 36 by 18, which is going to be 2, which give me y equals to plus or minus root 2. And if I put y equals to plus or minus root 2 in this equation, we get what? We get when y is plus or minus root 2, this gives me 4x squared plus 9 times plus or minus root 2 square equals to 36. This will give me 4x squared. So we get, so 9 times 2 is, so we get 9 times 2, so 9 times 2 is 18. So 18 equals to 36, which gives me x squared equals to 18, which gives me x equals to plus or minus 2 root 2. So now there are 4 combinations. All the 4 combinations are possible. Therefore, the points are so points of what? Points of consideration are So points of consideration are x with 2 root 2, y with root 2, 2 root 2, root 2, then again minus sign, plus sign for 2 root 2, minus sign for the other guy, and then we have next one is root 2, root 2, root 2, and 2 root 2 with the minus sign, and then we have minus of root 2. So these are all the possibilities for your solution. So let's figure out which one is maximum and which one. So since we have f of xy equals to xy, this implies f of 2 root 2 root 2 equals to f of 2 root 2 with a minus sign, root 2, because the minus signs will cancel out each other, is 4. And f of minus 2 root 2 root 2 equals to, now the minus sign for the other one equals to minus 4. So we get maximum value, and this will be minimum. So this is the method of Lagrange multipliers. All right, so now we can think about the same problem in function of three variables. So suppose we have f of xy and g of xy be the function with continuous first order partial derivatives. If the maximum and minimum value of the function f subjected to condition occurs at point P where grad P is not 0, then this happens. That means grad f equals to lambda grad P. So what should happen again is that the grad f should be parallel to grad g at P if P was supposed to be a extreme value. Of course, if grad P is not 0, if grad P is 0, then grad g at P is 0, then there's problem, right? You can't then apply Lagrange multiplier. So let's look at the following problem. Let's look at the problem which says find the first octant point P of x, y, z on the surface closest to the origin. So let's go about it. So in this case, what we have is, so we want to find out, consider the following problem. Find the first octant point P of x, y, z on the surface x square plus y square, x square, y square, z equals to 4 closest to the origin. So if you have a point in the space, the distance of this point, say the point coordinates of this point are x, y, z, then the distance is basically given by d. So again, d is a function. So d is a function of point x, y, z. It is square root of x square plus y square plus z square. So we want to optimize this function d. So closest to the origin, right? So minimize d of x, y, z subject to constraint x square, y square, z equals to 4. That's a good idea to label these axes properly. So instead of working with d, we will basically work with f of x, y, z equals to x square plus y square plus z square. Now we can do that here because d is always greater than or equal to 0. So optimizing for a positive is the same as optimizing for the square of it. So minimize f of x, y, z subjected to this constraint. So first we'll start with, so by theory of Lagrange multipliers, we know grad f should be lambda grad g subjected to, so what is my function g? So g of x, y, z, which is x square, y square, z minus 4 equals to 0. So this is a function I'm trying to optimize. Sorry, this is my constraint curve. So what is grad f? So grad f is going to give me 2x, 2y, 2z, right? That's what partial derivative of this with respect to x is 2x, partial derivative of f with respect to y is 2y, and partial derivative of z with respect to, of f with respect to z is 2z equals to lambda times grad g. Now, what is the derivative of this? This is going to be 2x, y square, z. We get x square, 2y, z, and we have x square, y square. So essentially we are solving. So the equations to solve are 2x equals to lambda times 2x y square z, 2y equals to lambda times 2 x square y z, and 2z equals to lambda times x square y square, along with another one.
along with x square y square z minus 4 equals to 0. So we are solving these together. So now the first two give us, so note x, y, and z are not 0. Why is that? Because first of all, if they are 0, they can't multiply to give you 4, right? If one of them is 0, and consequently none of them is 0. And also lambda is not 0 because, well, if lambda is 0, then x is 0. So this also implies lambda is not 0. Now, why are we considering that? So that we can divide by them and we can get rid of. So this too implies if you divide both of these, you get, or you can cancel off. So you get 1 equals to y squared z times lambda. And here you get 1 equals to lambda x squared z. If we combine these two together, equate the right-hand sides, you'll get x squared equals to y squared. Note that you could cancel lambda and z off because they are non-zero. So this gives me x equals to plus or minus y. This implies x, we'll consider since x, y, z belong to first octant, right? We're considering the first octant point, x equals to y, right? Now, what we want to do is the following. Let's solve these two together. So the way we'll go about it is the following. So we can divide both first equation by the second. We get y by z equals to, so lambda will cancel. You'll have, if you divide, we get y by z equals to, so x and x will cancel. We'll have 2 z. One of the y's will cancel. We'll have y in the bottom. So this will give us y square equals to 2z square. So now we have that. So from there we can get y equals to square root of 2z. Again, since we are considering z to be positive, so we can't have y equals to, so we have we can't have plus or minus z. We have y equals to square root of z. Right. So in that case, we have, now we want to find out what x, y, z are. So substitute this 1 and 2 in star. Okay, so when you substitute that in star, we get what? We get x square. So let's write x cube. So we have x square. So we have x square as x square, y square is x square as well. And we have z. Instead of z, we can write y by square root of z. Sorry, x by square root of z, because y is same as z. Sorry, y is same as x. So we have x equals to 2 times, so it's basically 4 because it's minus 4 equals to 0. So this is going to be 4. So this means x to the 5 equals to 4 root 2. This implies x is root 2. So therefore, what do we get? We get x, y, z. The point is going to be root 2, and z is going to be y by root 2, which is going to be 1. So this point is closest to, so this is a point closest to origin lying on g of x, y, z equals to 0. So this is our solution. Okay. So similarly, you can do the following. A and B, there are similar problem. They require a bit of, for example, problem A, you can see that's an ellipsoid and faces are parallel, means your function to optimize would be volume function v of x, y, z. You can see that's going to be 2x, 2y, and 2z. Okay. All right. So anyway, so now we can have Lagrange multiplier with two constraints. So the idea is the following. Suppose you have a function f of x, y, z, function of 3 variable. You want to find the extreme values of it, and you're subjected to two constraints. One constraint is g of xy equals to k, and the other constraint is h of xy equals to c. So how do we go about it? So this theorem tells us, this result tells us that if it happens at point P, then the relation we'll have is grad of f of P is lambda times grad P plus mu times grad of H. Why this is true, basically the idea is, suppose you're looking at, so first of all, you are looking at intersection of these two guys. So this surface is G equals to K. That means G of x, y, z equals to K. This guy is H of x, y, z equals to C. Now, essentially we are looking at the intersection. So our maximum or minimum value will lie on this intersection curve, which is C. Right. Now if f has an extreme value on this, then f of grad f is essentially perpendicular to, is orthogonal to C at P, right? And also naturally grad G is perpendicular to C, right? Because C is also part of the G, right? C can be defined as a curve which lies inside C, so it will be perpendicular to C, and in particular perpendicular to G at that point P. Okay, that's important. Similarly, we have grad of H is also perpendicular to C at P. So this means what? This means grad F lies in the plane spanned by grad H and grad G. So that means it's what? Grad F is a linear combination of these. So in this case, we have grad F evaluated at P is lambda grad G plus mu grad H, where lambda and mu are some constants. Yeah, so these are also again called Lagrange multipliers. So essentially, when you're solving for this, you are solving for the following. So you have fx, fy, fz equals to lambda times gx, gy, gz plus mu times hx, hy, hz. And then of course you have from here, and then you have another thing to satisfy is g of x, y, z equals to k, and h of x, y, z equals to c. So from the first equation, you can write down fx equals to lambda grad g plus mu grad h. So equating the first coordinates of this vector. Similarly, equating these coordinates of gives the second one, third one, and then you have g and h as the constraint. So solving this system